Hi, Professor McGuire here. I'm going to talk to you at the moment about circular buffering, circular arrays. It's more of a, or I would say more, it's as much of a matter of concept as it is a matter of programming. Meaning, once you understand the concept, then that's all you need. And but it's so important. The circular buffering is used absolutely everywhere. I made the comment. Uh, I believe uh, that there are literally hundreds and upon hundreds of circular buffers. I made in reference to queues, but they're all circular buffers that exist between me speaking and you listening, or me, making motions and you seeing. It's literally everywhere. And the reason is this. Actually, let me bring up. I can grab a slide, and I can show you something. So I'm going to put this up, and I will I'll share my screen. Okay. So, many of you know that I'm interested in digital signal processing. So, digital signal processing. This is a slide that I had shown in a class. What are the typical DSP algorithms that run? We have finite impulse response filters, by and large, the most popular method of filtering. So you want to do a low pass filter, you want to do a high pass filter for audio, let's say, and some bandpass filter. I mean, you're trying to limit the audio content. That's typically going to be implemented with a finite impulse response filter. And what we have here is this convolution operation is a multiplication between a bunch of coefficients, and I can show you on paper, and a Q. And that Q is implemented as a circular array. Infinite impulse response filters, so we have convolution, discrete Fourier transform, discrete cosine transform, all the compression algorithms that are operating between my speaking and your, being at the receiving location. That is all being done with those transforms. And those transforms are all doing these multiply accumulate operations that are operating on Qs that are specifically implemented as circular buffers. And so let's take a look at what a circular buffer is. So typically we've had our Qs, that exist as these lines, and so we have some order of elements, and so what we're doing is, so we're adding, and I can just make this easy and say we got, person one, person two, we use the typical queue where people are being added in, and then then someone dequeues, and so we have this issue of unless we move everyone up in the queue, this queue like shifts, and so then we have this these starting and ending locations, and so that's not a particularly, we don't like moving people along, okay, and we don't like people shifting. All right, we don't want the people waiting at the bank to go out the door, and at the same time, from a computational sense, we don't want to have everyone moving along, incrementally. And so the idea is that, what if instead of having this, and I'll just add, 6 and 7. What if instead we had basically formatted our memory space as if it were this, okay? And so so now we have person 1, person 2, person 3, person 4, person 5, person 6, person 7, and I'll add a 0 on here. so person 0, and so these are our locations now, okay? And so now we don't necessarily have to maintain this this issue of shifting things around, because everything's circular, okay? So there is no shifting, all right? What we're going to have is, if this is the front, okay, and this in this particular case is the back, all right, and then so this person has already gone, so they don't exist, all right, And so this is the front, and this is the back. And so, uh, um, so at this point, we're not full. Okay, so someone can be added at the back. All right, so someone comes in at the back, and now this is our new back. Okay, now we're full. All right, so someone DQs from the front. All right, so this is our new front, and then someone else DQs. So I'm going to get rid of that. Someone else DQs. All right, and this is our new front. And then someone else adds in, and we've got a new back, and so on. And so this situation can exist where we just have this rotating, and again, this is a conceptual thing. We just have this rotating, operation. Now, what it means in terms of this, we can implement this here. This is just a matter of sort of keeping track of things. Where when we reach a point where this, which was our back, now points here. Okay, and our front's here, and then so this is front, this is back. And then at some point, this front's here, and then the front's here, so these go away. And this is our new front. Oops. And then, this becomes the back. This, and so it's this concept that we can just, by keeping track of the indices, we can create this, what's termed a circular buffer, and it's termed it because you can either visualize it like this, or you can think of it operating circularly like that. And so this FIR filter that I mentioned here, mathematically, it looks like, I have a depiction here. Mathematically, it looks like this, where I have an input from an audio signal coming in here, digitized, and it goes through, it's multiplied by a coefficient, okay? And then that's my output. That's my first output. That's what's going on here. And then it gets delayed by 1. And so now I have a new audio input, and that gets multiplied by my coefficient that this delayed one was last time. Now this new one, the new one always gets multiplied by this coefficient. And then it gets delayed, and then on the next cycle, it gets multiplied by the next coefficient. And then it gets delayed. So 4 steps in, this is our newest sample, this is the last sample, this is the previous sample to that, this is previous sample to that. This is audio filtering. We can take recordings of your voice or your favorite song. We could run it through a 4-tap filter and make a low-pass filter, make a high-pass filter. This is a very real operation. But as you see, these coefficients, they don't change at all. But this is our cue, okay? And these values, the newest values always get multiplied by this coefficient. And we have these, the old next older value, next older value, next older value. As you might imagine, if we're doing video processing, we do not want to be shifting things within buffers, okay? So what's interesting then is the definition of a digital signal processor as a component is that it has to have single cycle multiply and accumulates. So this operation is going to be done in one cycle, okay? And that's not really related to our lecture, but it also has to have hardware circular buffering, and it has to have 0 overhead looping, okay, which means that circular buffering does not take extra clock cycles. Now, in our case, with our programming, we're going to take the extra clock cycles, okay, we have to, but in the hardware version of this, that's actually done with no overhead. And so it doesn't require any extra operations to achieve that. And so that's what you're doing when you're doing circular buffering, is you're creating the situation where you no longer have to shift things. Okay, everything, the goal here is that everything takes a single operation. So I hope that helps to clarify what circular buffering is. Thanks so much.